This is the famous Riemann-Zeta function. We will be looking at it for values of x that are real, specifically values greater than 1. And we want to show for values greater than 1 that this sum exists. So it's finite. So I can write, less than infinity means it converges to something. This is not entirely obvious because when we take x equals 1, this does not converge. We obtain the harmonic sum, which, as you know, does not converge. And I did this in a previous video, so I will leave a link to it. But it's not entirely obvious if this converges with a value of, say, 1.001. But it does, and we want to prove that it does. The proof uses some really interesting series manipulation techniques, and I'm sure you will like it. In fact, the function zeta x, or zeta z in the complex plane, has some really interesting properties, as you may imagine. When does the sum of a series exist? Well, you could say a series sum exists, or the series converges, when the sequence of partial sums converges to a limit. So here are the first few partial sums of our Riemann zeta function, our real Riemann zeta function. Okay, I have S1, S2, little s3. These are partial sums. I take the first 3 terms here. And how about the nth partial sum? And here's the nth partial sum all the way up to 1 over n power x. Now, if we examine these things carefully, we see we're starting with 1, and we keep adding, start with 1, and we're adding little positive terms here. Keep accumulating positive terms on top of positive terms. That means that these partial sums are getting bigger. S1 less than S2 less than S3 and so on. So Sn is less than Sn plus 1. N plus 1 is always going to be bigger, strictly bigger than Sn. So I can say that this sequence of partial sums from 1 to infinity, well, this is a strictly monotone increasing sequence. So I put the little arrow like this for strictly monotone increasing. And if I have a strictly monotone increasing sequence, well, I can apply the monotone convergence theorem. In fact, it doesn't even have to be strictly to use the monotone convergence theorem, but in our case it is strict, so that's nice. So the MCT, monotone convergence theorem, says the following. If I could find an upper bound for my sequence of partial sums, that's enough to show that the limit exists. And there we go. The limit exists. That means the original sum exists, because the original sum, zeta x, that's just the limit of the partial sums. So we can understand MCT in a kind of intuitive way like this. Let's say my sequence is getting bigger in this direction, and there's this wall here that it cannot go across. So there's this barrier, and this barrier is called the upper bound. These points cannot cross this upper bound. So because of this, and because it's strictly monotone, so they're always increasing. They're actually not even staying still. They're always increasing, although if they are staying still, then it reaches a limit in a different way. But they're definitely not going back on each other, so there's no oscillations or anything. So at some point, you have to accumulate to a limit. They cannot keep getting bigger and bigger beyond this upper bound, but they are getting bigger and bigger in a strict sense. So you think about this. This is a very interesting way of looking at MCT. Well, beyond that, I want to say a few words about MCT. I think there's a tendency to underestimate how powerful MCT is and how important it is. You can do some very nice proofs in an elegant way using it if you can exploit it. Also, I think knowing this theorem and knowing how to prove it greatly helps with understanding analysis. It greatly helps with your intuition about analysis, which, that's kind of a tough topic to gain an intuition about. And if you want this kind of intuitional feeling about analysis, I would say, well, start learning Monotone Convergence theorem, learn the proof for it. In fact, I might do some videos about it in the future. It's such a great and important theorem. Here's our typical partial sum Sn, and I want to do something with this. I want to make an even partial sum, and by that I mean partial sum that has an even number of terms. That's easy enough to do. I just keep going with these terms all the way up to the 2nth term power x. So this is even here, 2n. So I've created it to be explicitly even. Now let's make an alternating version. In the alternating version, the even terms here, these even terms will be negative. So let me call that t. 2n. Alternating, because there's a t here, and s for just plain old sum. It's kind of lame, but it's a good enough mnemonic. It'll work. All right, 1 minus 1 over 2x plus. Okay, the next one is negative. 1 4x plus dot dot dot. And the last one, what should that be? Plus or minus? Well, the last one is even, so it has to be negative 1 over 2n power x, like that. In fact, let me take a bit more here, one more term, just to show you, okay, the term before it is positive because it's odd, and then the term coming after 2nx, that's even, so that's got to have a negative. Now let's take a sequence of an even amount of numbers. So here I've got 8 numbers. And what I can do is pair up the stuff inside. And then I can pair up the last two like that. So I can always do this when I have an even number of terms. And so let's apply this idea to T2n. I will group the terms in T2n in a clever way, this way here. All right, so I've done some grouping here. Okay, so I did this term. Now I grouped those two, and I grouped 4 and 5 over here. Okay, and let me finish up with the end. Okay, I have this one here, which is even, so there's a negative in front. And then I have the last term, which is handled separately like that, 2n, that's negative, power x, like so. Right, okay, so now I'm going to factor out all these minus signs. Right, okay, so I've taken out all the minus signs. I get that. Okay, not bad. And if I look carefully in here, this is positive. This is positive. This is positive. All are positive. And in fact, inside here, underneath this, this is positive too. So I am starting with 1. I'm starting with 1. And everything that I'm subtracting here is positive. So what this means is that T2n has to be less than 1, strictly less than 1. These are not 0. So that's our first very important fact that we've discovered. It starts off with 1, and I keep subtracting off stuff. And so, of course, T2n has to be less than 1. I can write it like this. T2n is 1 minus all this positive stuff. So, of course, there's no negatives in here, so I don't have to worry about it inadvertently getting bigger than 1. It's just going to be less than 1. So I proved this fascinating fact about this alternating series. Now, if you like this alternating series stuff, well, check out the links that I'm going to put in the description box, because I have a couple of other videos where I do alternating series, and I use this kind of rearrangements of terms to prove interesting things. And one of the interesting things that I ended up proving in one video is that E is not rational. So that can be proved in a beautiful way by alternating series. So check out those links. Starting again with our alternating series T2n, let's do another clever transformation. So this T2n here, this is actually equal to the following. I can begin with my original Zeta series and subtract off some stuff. What happens if I subtract off the following? Okay, does this work? If I subtract off all the even terms, well, it doesn't really work because then the even terms are going to just become a 0 here. So that doesn't really do what I want. What I want is this, put a 2 here. And now if I subtract off 2 of them, well, this is going to change all the even terms from positive to negative, you see? And so this works. But this actually was my original Zeta series, so I can write it like this. Like so. So I just put S2n for this series here. This is my even Zeta series. Now let's continue to do some transformations. This is S2n minus 2. Now if I remove 1 over 2 power x, I have a 1 here, plus 1 over 2 power x, plus 1 over 3 power x, plus ... and this is 1 over n power x. And so what do I finally get? Well, T2n is equal to S2n minus 2 over 2x Sn. Wow, what an amazing formula. So I have written the alternating series in terms of the original series and the original series, but an even number of terms. And you say, okay, well, what does that give me? Well, you do remember that we proved T2n is less than 1. So we see here that there is a good chance we might be able to find some kind of bound. All right, let's make some room here. The first point, A, is that this partial sums Sn, this is strictly increasing. And so this implies that S2n is actually strictly bigger than Sn. We can now put that in here and obtain an inequality. Like so, T2n has to be bigger because this is bigger than this. And why did I do this? Well, now I can factor out the partial sum Sn, you see. However, we have another point to consider. We proved this, the alternating partial sum T2n, that's less than 1. So that has implication on this also. So I can write it like this way, backwards, like this. But we also know this. So this is greater than Sn minus 2 over 2x Sn. All right, let's make a bit of room. Then we know by combining this part of the inequality with this, we know the following. We know this, which is very good, and we can continue with this. Let's factor out Sn. We get this. Okay, I can change this around a bit. I can write like this, 2 power x minus 2 over 2 power x. And then finally, I could do one more transformation. Sn, partial sum Sn is less than 2 power x over 2 power x minus 2. And this is what we've been looking for. This is the goal. This is our upper bound. We did it. So Sn is bounded. You just plug in the value of x that you're using, and Sn has to be smaller than that for any n. And so therefore, by monotone convergence theorem, the zeta function, real zeta function at x exists because the limit of Sn exists. So this exists, is some limit c, or you can just call it little s like this. So we are done with that part of the proof. Well, we're done with the proof. I just want to illustrate some things in the next part. But I think this is a magnificent calculation with an amazing result. I think this upper bound is kind of surprising, how the way it emerges from our transformations of the series. It's very, very, very beautiful formula. All right, let's look at it and let's see it in action. I was curious to see what happens with this upper bound numerically. So I took the first million terms of the Zeta series and I truncated that, and I call it, okay, let's call it Zeta wiggle. And I took some integer values of x. Anything bigger than 1 is good. I could take 1.01, but I just took integers. And then I evaluated the upper bound formula. And what did I get? Here are my results. And let's look at it. So when x is 2, the upper bound is not that great. You see, zeta of x is 1.6, but upper bound is 2. But as we get larger, the upper bound is pretty good. It's pretty sharp. So I'd say that this upper bound is really nice. It's really good as x gets larger. Well, I'd like to leave you with a project to think about. As x goes to infinity, what happens with zeta x and this upper bound x? What's the relationship between them? I think this is a very interesting question, so I'll let you think about it. And as always, like, comment, and subscribe. And don't forget to watch those videos about alternating series that I did previously. They have a lot of really good stuff in them that you will enjoy. And I will see you next time.